Imagine a volcanic rock billions of years old being transformed into one of the most valuable building materials in the modern world. In a factory in Denmark, furnaces reach temperatures of 1500 degrees Celsius, hotter than volcanic lava, melting solid basalt until it becomes a golden river of liquid rock. Within seconds, this incandescent mass is transformed into fibers thinner than a human hair, creating a material that can resist fire for hours, insulate buildings against Arctic cold, and absorb sounds like a perfect acoustic sponge. How is it possible that a common rock, found abundantly in the Earth's crust, becomes the foundation of a $12 billion industry? How are millions of tons of basalt processed daily to create a material that protects skyscrapers, homes, and industrial facilities around the world? The answer lies in one of the most fascinating and technologically advanced industrial processes of our time: the manufacturing of rock wool. This is not just a common building material. It is the result of decades of innovation, precision engineering, and a deep understanding of materials physics. Each fiber produced carries within it the ancestral strength of the volcano and the sophistication of modern technology, creating a perfect symphony between nature and science. The history of rock wool begins millions of years ago, when active volcanoes naturally created the first rock fibers through violent eruptions. The inhabitants of Hawaii were the first to observe this phenomenon, finding golden and silky fibers, known as Pele's hair, formed when wind stretched drops of volcanic lava into thin filaments. In the late 19th century, American inventor Charles Corridon Hall observed these natural fibers and had an epiphany. If nature could create this material, why not replicate the process industrially? In 1897, Hall patented the first method to produce artificial mineral fibers, establishing the foundations for a revolution in civil construction. The true transformation came in 1937, when the Danish company Rockwool developed the first commercially viable process for mass production. During World War II, demand for insulating materials grew exponentially, driven by the need to protect buildings against bombing and keep military installations heated in extreme conditions. The 1950s marked the beginning of the modern era of rock wool, with the development of high-temperature rotary furnaces and centrifugal spinning techniques. The discovery that different types of basaltic rock produced fibers with distinct properties led to a scientific race to identify ideal mineral compositions. In the following decades, the industry evolved from an artisanal process to a highly automated operation, incorporating computer control, real-time chemical analysis, and quality systems that ensure microscopic consistency in every fiber produced. The process of transforming basalt into rock wool is a complex dance between chemistry, physics, and precision engineering. Everything begins in quarries, where basaltic rocks are extracted and carefully selected based on their specific chemical composition. Ideal basalt contains approximately 45% silica, 15% alumina, and a precise mixture of iron, magnesium, and calcium oxides. At the factory, rocks pass through a primary crusher that reduces them to fragments of 10 to 15 centimeters. These fragments are then fed into cupola furnaces, imposing structures 8 meters high, lined with special refractory bricks that can withstand extreme temperatures without deteriorating. The heart of the process is fusion. High-power burners, fed by natural gas or coke, raise the internal temperature of furnaces to 1500 degrees Celsius. At this infernal temperature, solid basalt transforms into a homogeneous liquid mass, with the consistency of hot honey. Chemical composition is continuously monitored through automated spectrographic analyses. The molten rock flows through refractory channels until reaching spinning machines, the true technological heart of the operation. Here, liquid rock is poured onto spinning wheels that rotate at speeds of up to 3,000 revolutions per minute. Centrifugal force projects the melted rock through thousands of small orifices, creating continuous filaments. Simultaneously, high-velocity compressed air jets stretch and cool these fibers, solidifying them in milliseconds. The result are fibers with diameters between 3 and 8 micrometers, invisible to the naked eye, but with extraordinary properties of resistance and flexibility. Modern rock wool production represents the pinnacle of materials engineering. incorporating technologies that seemed like science fiction just a few decades ago. Current furnaces utilize pure oxygen combustion systems, increasing thermal efficiency by 30% and drastically reducing gas emissions. The most significant revolution came with the introduction of artificial intelligence-based control systems. Infrared sensors monitor molten rock temperature with 1 degree Celsius precision, while machine learning algorithms automatically adjust feeding speed, spinning wheel rotation, and airjet pressure to optimize fiber quality. Real-time X-ray analysis technology allows operators to monitor the chemical composition of molten rock and make instant adjustments by adding specific minerals. This ensures that each batch of rock wool has identical properties, regardless of natural variations in raw materials. One of the most impressive innovations is the three-dimensional formation system for blankets. After spinning, fibers are collected on moving belts, where they receive a controlled application of thermosetting resins. Computer vision systems map fiber distribution in real time, ensuring uniform density throughout the product extension. Curing ovens represent another technological leap. Using electromagnetic induction heating, they cure resins uniformly, creating a stable three-dimensional structure that maintains its properties for decades. Humidity and density sensors continuously monitor the process, adjusting temperature and curing time for each product type. Quality in rock wool production is an obsession that permeates every aspect of the process. Laboratories equipped with scanning electron microscopes analyze fiber samples every 15 minutes, measuring diameter, length, and structural integrity with nanometric precision. Quality control begins even before production, with detailed geological analysis of quarries. Each Basalt shipment undergoes complete chemical analysis, using X-ray fluorescence spectrometry to determine the exact composition of more than 20 different elements. During production, automated sampling systems collect fibers directly from production lines for thermal resistance testing. Samples are subjected to temperatures up to 1,000 degrees Celsius to verify they maintain their structural integrity, a critical requirement for fire safety applications. Thermal conductivity tests are performed in special climate-controlled chambers, where samples are exposed to controlled temperature differences. High-precision sensors measure heat transfer through the material, ensuring each product meets thermal insulation specifications. Compression resistance is tested through hydraulic presses that apply gradual loads up to 50 tons per square meter. These tests simulate extreme conditions the material may face in structural applications, ensuring it maintains its insulating properties even under pressure. Digital traceability systems record every process step, from rock origin to final product. Unique QR codes allow tracing any quality issue to its specific source, facilitating continuous process improvements. The rock wool industry has embraced sustainability as both an environmental and economic imperative. Basalt, being one of the most abundant rocks on Earth, offers a natural advantage. Reserves are practically inexhaustible, with estimates that current quarries can operate for thousands of years. Energy efficiency of modern furnaces represents a significant advance. Heat recovery systems capture hot exhaust gases and use them to preheat combustion air, reducing fuel consumption by up to 25%. Some manufacturers have implemented cogeneration systems that convert residual heat into electricity, making factories partially energy self-sufficient. Waste management follows circular economy principles. Production scraps and rejects are reintroduced into the melting process, eliminating practically any material waste. Even dust collected by filtration systems is reprocessed, ensuring total raw material utilization. Sustainable packaging innovations include the use of biodegradable plastic films and compaction systems that reduce transport volume by 40%. This results in lower logistical carbon footprint and significant reduction in fossil fuel use for distribution. Reforestation programs in mining areas transform old quarries into thriving ecosystems. Some companies have developed techniques to use rockwool waste as substrate for plant growth, creating artificial soils rich in minerals. Research in bio-based materials is exploring the use of plant-derived natural resins to replace traditional synthetic binders, potentially making rock wool 100% natural and biodegradable. The development of modern rock wool faced challenges that tested the limits of engineering and human creativity. One of the first obstacles was broken fiber syndrome, a problem where fibers fragmented during the spinning process, creating microscopic particles that compromised product quality. The solution came through years of fluid dynamics research. Engineers discovered that the exact angle of air jets and cooling speed were critical. They developed special nozzles with geometry optimized by computational simulation, which create controlled turbulence to stretch fibers without breaking them. Another monumental challenge was controlling chemical composition during fusion. Different types of basalt reacted unpredictably when mixed, creating variations in fiber properties. The solution involved developing mixing algorithms based on statistical analysis of thousands of different combinations. The problem of equipment corrosion at high temperatures almost made industrial-scale production unfeasible. Traditional furnaces lasted only a few weeks before requiring costly repairs. The breakthrough came with the development of multi-layer ceramic coatings and cooling systems using inert gas circulation, extending equipment lifespan to years. The environmental issue of particulate emissions required innovative solutions. Multi-stage electrostatic filtration systems were developed specifically to capture rock particles with efficiency superior to 99.9%. These systems use high-voltage electric fields to ionize and capture even the smallest particles. The logistical challenge of transporting a bulky and relatively light material led to the development of reversible compaction techniques, where rock wool is temporarily compressed for transport, and then recovers its original shape at the installation site. Rock wool has transcended its origins as a simple insulating material to become an essential component of modern infrastructure. In skyscrapers, it forms invisible fire barriers that can contain fires for up to 4 hours, giving sufficient time for evacuation and firefighting. One World Trade Center in New York uses more than 2,000 tons of rock wool in its passive fire protection systems. In the petrochemical industry, rock wool protects pipelines that transport substances at temperatures up to 700 degrees Celsius. Refineries around the world depend on this material to maintain energy efficiency and operational safety. A single refinery can use up to 10,000 cubic meters of rock wool in its insulation systems. The data center revolution brought an unexpected application: acoustic control. Rock wool absorbs noise from thousands of servers, creating quieter work environments and reducing urban noise pollution. Major technology companies report reductions of up to 15 decibels in their facilities. In shipbuilding, rock wool protects vessels against fires and improves acoustic comfort. Modern cruise ships use special versions resistant to marine humidity, ensuring lasting protection even in extreme oceanic conditions. Hydroponic agriculture discovered in rock wool an ideal substrate for plant growth. Its porous structure retains water and nutrients while allowing excellent root aeration. Urban vertical farms produce vegetables year-round, using this material as a growing base. Aerospace applications include thermal protection of rocket and satellite components. Rock wool's ability to maintain its properties in the vacuum of space makes it ideal for long-duration missions. The future of rock wool is being shaped by revolutionary advances in nanotechnology and smart materials. Researchers are developing fibers with adaptive properties that can alter their thermal conductivity in response to temperature changes, creating self-regulating insulation systems. Integration of microscopic sensors into fibers promises to transform rock wool into a smart material capable of monitoring the structural health of buildings. These sensors can detect movements, temperature variations, and even the presence of dangerous gases, transmitting real-time data to building management systems. Advances in biotechnology are exploring the use of microorganisms to produce mineral fibers through biological processes. Genetically modified bacteria could secrete compounds that crystallize into fibers with properties superior to those produced conventionally. Three-dimensional printing with rock wool is emerging as a real possibility. Controlled deposition techniques would allow creating insulating structures with complex geometries impossible to obtain with traditional methods, optimizing thermal performance for specific applications. Research in hybrid materials combines rock wool with graphene and carbon nanotubes, creating compounds with exceptional electrical conductivity and mechanical resistance properties. These materials could revolutionize electronics, enabling devices that dissipate heat more efficiently. Space exploration is driving the development of ultra-light versions of rock wool for use in Martian habitats and space stations. The abundance of basalt on other planets makes this material a natural choice for extraterrestrial construction. The journey of rock wool, from primordial volcanic eruptions to today's high-tech laboratories, represents one of the most remarkable material transformations in human history. What began as a natural curiosity observed in Hawaiian volcanoes evolved into a $12 billion global industry that protects and insulates practically every aspect of modern life. Each rock wool fiber carries within it millions of years of geological history and decades of human innovation. The process that transforms solid rock into protective material in a matter of minutes is a testament to humanity's capacity to master nature's forces through science and engineering. The technological complexity involved, from furnaces that replicate conditions inside the Earth to artificial intelligence systems that control every aspect of production, demonstrates how the pursuit of industrial perfection can lead to advances that benefit all of society. Rock wool is not just a product, it is a bridge between the natural and built worlds, a solution that allows humanity to live and work safely in increasingly complex and challenging environments. Its silent presence in our walls, ceilings, and structures is a constant reminder of how innovation can transform the common into the extraordinary. The impact of this industry goes far beyond financial numbers, touching fundamental issues of safety, energy efficiency, and environmental sustainability that will define the future of civil construction and fire protection. How incredible to discover how something as common as volcanic rock can transform into the silent guardian of our lives. The next time you enter a building, remember that millions of microscopic fibers are working tirelessly to keep you safe, warm, and protected. What impressed you most in this journey through rock wool manufacturing? Was it the extreme temperature of the furnaces, the microscopic precision of the fibers, or perhaps the futuristic applications being developed? Leave your comment below and share which aspect of this incredible transformation most sparked your curiosity. Do you know someone who works in civil construction or who simply loves discovering how things are made? Share this video and help spread the fascination for the engineering that makes our modern life possible. And if you're eager to discover more industrial secrets, don't forget to subscribe to the Factory Made channel, where each video is a new adventure through the world of manufacturing. What other construction materials would you like to see unveiled? High-performance concrete? Tempered glass? Or perhaps something completely different? Your suggestion could be the next episode we explore together in this fascinating journey through the world of how it's made. Special thanks to Rockwool International, Saint-Gobain, and Paroc Group companies for making available technical materials and images of their industrial operations that made possible this detailed exploration of the rock wool world. Gratitude also to engineers and materials specialists who dedicate their careers to the continuous improvement of these fascinating processes. We thank materials research institutes and technical universities that share knowledge about rock wool properties and applications, contributing to scientific advancement that benefits all of society. And most importantly, our sincere thanks to you, who dedicated your time to follow another exploration of the factory-made universe. Your curiosity and interest are the fuel that motivates us to continue unveiling the secrets behind the materials that shape our world. Continue with us on this journey of discoveries. Explore our other videos about industrial manufacturing and discover how seemingly simple products hide processes of surprising complexity and beauty. At Factory Made, each story is a celebration of human ingenuity and the magic of industrial transformation. Research and script by Factory Made team, transforming curiosity into knowledge, one process at a time.